So we basically looked at, finally we came to some results from the lattice QCD approach. And first we had looked at, for example, the thermodynamic pressure, the energy density, entropy, right? These are the basic quantities as they vary with temperature. And what we said that there are two extreme limits which one could think of where this complicated QCD framework kind of simplifies. And so at the low temperature, rather at the high temperature regime, you have this non-interacting quark and gluons system, which one can easily write down the partition function, and you should get pressure of this expression and the other quantities. You are supposed to work them out, and you'll get some similar simple results. So here that limit is being indicated by this line over here. So it's also sometimes called as a Stefan-Boltzmann limit, right? So that's one limit, and then there is the other limit which comes right and in the low temperature regime, and we said that here this what is known as the HRG, or the Hadron Resonance Gas, which is again a non-interacting gas, but now not of quarks and gluons, rather colorless objects, your hadrons and other heavy resonances, right? So, and as you see, there is a very remarkably very nice agreement between these HRG model and the lattice QCD results on this side. Of course, in this side, as we said, that at temperatures 400 MeV or so here, there is a sizable deviation from the non-interacting limit, which could be signifying that there are still some interactions. The quarks and gluons are not completely like non-interacting, but there is still interactions going on. And it is expected, I mean, from current calculations, which go on to much higher temperatures, the current consensus is that you really need to go to a very, very high temperature to achieve this kind of limiting results. So here it kind of almost rises very, very slowly. Okay. So we did discuss this high temperature limit, and there we stop today. Let's just discuss a bit more in detail what is this HRG phase, because that is a very important model as concerned the phenomenology of heavy ion collisions, right? Because this regime is very, very important whenever you want to do any phenomenology with heavy ion collision observables. And in that regime, as you see, the HRG model assumptions become quite good, and hence it is important to understand this model in more depth. So at low temperature, right, so there is color confinement in QCD, and hence the degrees of freedoms instead of quarks and gluons now are hadrons, right? So the hadrons, so these quarks and gluons now get confined hadrons, right, in colorless hadrons. And we have two types of hadrons, basically baryons and mesons, depending on their spin. Statistics follow, so the mesons follow the Einstein statistics, while the baryons follow the Fermi-Dirac statistics, right? So they become relevant degrees, of freedom in the region, right? So this model has been prescribed long ago, and it is
recording in progress.
We have this partition function in the Hadron Resonance Gas model, And this is your standard ideal gas thermodynamics, which you must have studied in your statistical mechanics course, for example, Patria level, right? So what you do if you have a gas of non-interacting species, the logarithm of the total partition function, you can just write as a sum over the logarithm of the individual partition function of the, individual partition functions, right? So that's how we write it right down here. Um, and that's because the partition function itself is a product of the individual species. So when you take log, it becomes a sum over the log, right? So the mesons and the baryons have been written down here separately because their expressions are slightly different, right? So this is the detailed expression. So basically there is this difference in the sign here and so here. So it's just because of the different statistics that they follow, right? So so here the informations of the hadrons that go into this partition function, as you see, is that their masses, right? And also their quantum numbers, right? What is the baryon number of that hadron? What is the electric charge of that hadron? What is the strangeness of that hadron? Um, Here there is also a degeneracy factor, which is somehow missing over here. So there is a degeneracy factor, for example, depending on the spin and so on, you will have 2s plus 1 and so on and so forth, right? Factors, that means degeneracy factor. Right. So this is so given this expression of the partition function, again, by the simple relation between the partition function and thermodynamic quantities, you should be able to evaluate these individual quantities within the framework of the Hadron Resonance Gas model, right? Okay, so once, so that's the low temperature uh, uh, approximation to which the lattice results seem to very nicely overlap with, right? Now, this model becomes very handy when we want to extract information about freeze out, for example, the freeze out temperature, freeze out chemical potential by comparing with experimental data, which we will come to later. Okay, so for now, this is just the introduction to this phase. And so let's now put them all together on this so-called this QCD phase diagram, right? So we have been so long, we have been only talking about this temperature axis, right? That's what we were showing here, right? This is the temperature axis. And I said that there is a sign problem to, to go from zero to non-zero chemical potential. But then I also mentioned that lately there have been a lot of progress. People have tried to circumvent the sign problem by one of the method was stellar expansion, for example. And with that, now we know some parts of even the non-zero mu B phase diagram, let's say, right? So first of all, so this is the usually the phase diagram that you will see in many presentations or paper. So let's try to just go through the various aspects of the phase diagram that one should be aware of. So QCD has three conserved charges, right? So it has baryon, net baryon as a conserved charge, usual energy, right? In any theory, energy is always a conserved charge, conserved quantity. And in addition to that, QCD being QCD, okay, SU3 non-abelian gauge group. So all those mathematics, somehow the physics manifestation is that you have these three conserved charge, what we call as baryon, net baryon, net electron. And canonical ensemble, right? When you do the statistics of such a system with three conserved charges, conserved charges, right, apart from energy, you will need the corresponding Lagrange undetermined multipliers, right? For energy, you have this parameter, what we eventually call as temperature, and for the three conserved charges, you will now have three chemical potentials, right? Mu B, mu Q, mu S. So the most general QCD phase diagram, if you were to think, you should think of it as a four-dimensional phase diagram, right? Because you can have a temperature, you can have mu B, you can have mu Q, and you can have mu S as independent axes in that phase diagram, right? As independent parameters. So the most general thermodynamic state of QCD, if you have to specify, you have to give all these four values, right? What is the temperature? What is the mu B? What is the mu Q? What is the mu S? So then the question is, then why in our community, in the heavy ion community, why we don't usually look at this four-dimensional diagram, but always refer to this 2D picture with T and mu B, right? So in order to go from this four-dimensional phase diagram to this two-dimensional phase diagram, what you have to keep in mind is the following. So since we are limited to QCD matter as accessible in heavy ion collision, right? So we are actually constrained or bound by the initial conditions of the incoming nuclei, right? So the two nuclei that are colliding, they will decide what are the conserved charges this medium which will be formed after the collision, what are the conserved charges that medium will contain, right? So, of course, the nuclei are all net strangeness zero nuclei, right? So that means the fireball that you will create, right, will have net strangeness zero, right? It cannot have a non-zero net strangeness, right? Because QCD interactions will conserve your strangeness, right? And then also the ratio, now it can have net baryon charge, right? Because the nuclei itself will have how many proton and how many neutron. If you add them up, the mass number, that's kind of the net baryon of that medium, right? And also it will have net electric charge because the number of protons it contains, that nuclei, right, that gives the positive charge to it. However, you see, they are not independent, right? Because the incoming nuclei, it will have a certain net baryon and a certain net electric charge. And very, I mean, strangely enough, if you look at all the nuclei that we collide, say gold, lead, uranium, okay, and others, and if you look at their net baryon to net electric charge ratio, you will see that they will be roughly near about 2.5, right? So in the theory, in the modeling phenomenology, we usually just take it to equal to 2.5, right? So we already have these two conditions, right? And which means that you are basically in a heavy ion collision experiment, you are mostly exploring a two-dimensional slice, right, of this originally four-dimensional phase diagram, right? And so usually what is done is that the mu q, so this fact that net strangeness is zero means it fixes your mu s, and this condition is used to fix your mu q, right? And so you are eventually left with T and mu B as your free parameters in the model, which you can play around with and try to see where you are, okay, when you want to compare with a given experiment, right? Given experiment means from one experiment to another experiment, uh, the main difference could be the beam energy, right? The energy with which you are colliding the two nuclei. That basically is the argument behind why we mostly concentrate on this 2D phase diagram made up of in the T and mu B plane, and we mostly forget mu S and mu Q in most discussions. Okay, so that's a QCD phase diagram, and now so that's about the dimensionality. Now let's try to observe, okay, what are closely the various features that are there on this QCD phase diagram, right? So one thing is what we have already discussed, that you see at these low temperatures, right, and also these low baryon chemical potentials, what you expect is a hadron gas, right? Hadron resonance gas. And then at this high temperature, right, and maybe even at very high densities, right, what you expect is the quark-gluon plasma phase, right? So then our standard, if you extrapolate and interpolate things, you can then imagine that there must be a regime where these hadron, or rather colorless degrees of freedom, right, are changing. There is some change or rearrangement is happening, and we are giving rise to degree of freedom, right? Now, strictly at this zero chemical potential, this change is happening with change in temperature, right? Which is very well studied and very well understood now, and which was represented here, right? So, this temperature, right, where this transition is happening, right, this here is indicated like this, about 155 MeV, where this transition, this dashed line is meeting this temperature axis, right? So we will come to this 155 MeV, and I mean, does it make sense to talk of one number here? Because there is strictly no phase transition, right? There is no discrete jump, right? There is a smooth transition. So which point do you actually pick up and say, oh, here is where the hadrons have become quarks, right? So you can always say that. So then does it then justify to quote one number? So that is one interesting question we could ask, which we will indeed ask and try to expand on that. And then as you now leave the zero baryon chemical potential regime and come towards non-zero baryon chemical potential, with the latest inputs and developments on Lattice QCD side, these Taylor expansion methods and other methods, up to reliably up to certain mu b by t, okay, say 2 or 3, um, I mean, there are results, and so there is agreement up to certain regime, and beyond which various groups have various estimates. So some groups claim that they have already come across a critical point, while some groups claim that they have not yet seen a critical point. So regarding the existence and the location of this QCD critical point, where the phase transition, right, instead of being continuous, is expected to have a second order phase transition. So you expect to see divergence in the second order derivative of the partition function, right? Or the pressure. So like susceptibilities. So there is still a ongoing, I mean, discussion regarding the exact location in the QCD community itself. So while at very large baryon chemical potential, most models and from symmetry arguments, there is very strong reason to believe that there must be a first order phase transition, right? So that means there will be a discrete jump in the and go across this chemical potential. However, these regimes are still not accessible to lattice QCs and various approximations. And in that framework, there are these suggestions. So yeah, so these are some of the features, and of course, our very important, one of the very important goals in heavy ion collision experiments is to throw light, right, about the existence of these features, and if they're there, their exact locations, and so on and so forth, right? And also, mind you, so long we have been only discussing equilibrium QCD matter, right? So that means it's like if you have a tank and you have water in the tank and it's sitting quietly, right? And you slowly heat it and or slowly cool down it, and you are looking at it, whether it is freezing, whether it is remaining fine, or whether it's starting to vaporize. But we don't have that freedom, right, or the comfort with the firewall in the heavy ion collision experiment, right? It's a very fast thing, and there is a the complete global equilibrium is a very strong approximation there, not at all true. So at most one could extend these ideas of equilibrium to say a local thermal equilibrium and then try to construct models, and that's what has been mainly done. So then questions can be that these first principle calculations are for a completely equilibrated matter, right? Which a matter which is in thermal and chemical equilibrium, right? Because only then it makes sense to represent that matter as a point on this phase diagram, right? Because you are saying when you are putting a point here, you are saying it is at a temperature this, it is at a chemical potential this. So it's an equilibrium ensemble, right? Now, the heavy ion collision firewall is rapidly evolving, and uh, whether the framework that is used to discuss or explore this equilibrated matter, how much of that framework uh, can be extended to study a rapidly evolving firewall, that is also questionable. And of course, there have been various developments. Okay, so with those comments, let's now nevertheless try to understand what all we know, for example, in the complete this equilibrium picture, right? For example, in lattice QCD. So what we know now in a very confidently from the lattice community is that the chiral crossover temperature, right, in this 2+1 flavor physical QCD, okay, is this 154 plus minus 9 MeV, right? So this is the extrapolation. So in this plot, if you closely see, what is there is that there is this n tau to the power -2. So yesterday we said that what is n tau? It is basically the number of lattice intervals or points that are there in the tau direction, right? And what you see here is that they are trying to go to larger and larger n tau, right? Because this is n tau to the power -2. So smaller this is means larger the n tau. So that means you are now having more and more points, right? To do a better numerical evaluation, estimation of your lattice, right? And then this TC, or don't confuse this TC with T critical, right? It's not the critical point temperature, please, okay? This is the chiral, this C is getting its name from the fact that it is the chiral crossover temperature. Okay, and not don't think of it as a critical temperature. So this calculation is for mu be 0. Okay, so and you see now as they are going to more and more finer lattice, this estimate, right, is changing, and then eventually it tries to get saturated, and so they know their statistics and their systematics, and this is the with the best results are that they can tell with this kind of accuracy. The same thing with these blue points, and the difference between the red and the blue points are that one is this HISC action, the other is this ASQ-TAD action. So basically, on the lattice, when you put the QCD Lagrangian, you are basically discretizing the QCD fields, right? The gluon fields and the fermion fields. So so these are basically different ways you could discretize the same continuum QCD action on Lagrangian, right? So of course, in the continuum limit, that means when the size of the discreteness goes to 0, if you are sure of your systematics of the different discretization scheme, the difference in the discretization scheme you expect to disappear and give you a result which overlaps, right? So then you are confident that the result that you get doesn't depend on the scheme in which the scheme that you choose to discretize, right? Because that scheme is your choice. Nature has no idea, right? So if you are doing things correctly, your final result should be scheme independent, right? How you discretize. And that's indeed this result show, and hence with quite a confidence they can claim that this is the chiral crossover temperature in 2+1 flavor physical QCD. So let's try to um, understand briefly these various meanings. So 2+1 flavor physical QCD refers to the fact that up and down quarks, which are the lightest quarks, right? Their masses have been taken to be same, right? And then there is this +1, which means there is this strange quark, and its mass has been taken to be whatever its physical mass, right? So that's the framework. And indeed, you will agree that for our heavier collision, that is good enough, because even the heavier ones like charm, bottom, they do not take part in the thermodynamic thermodynamics. Right? They are too heavy. So that's the 2+1 flavor physical QCD. And the chiral, now crossover temperature we have already discussed, but then there is this chiral, right? So usually when you try to characterize a phase transition, you look for an order parameter, right? If there is a true phase transition, usually there is a change in the symmetry, and there will be some order parameter, right, which will be 0 in one phase, and then it will become non-zero in the other phase, right? And the point where it becomes non-zero, then you identify and you say, okay, this is with that order parameter, you identify, okay, this is my phase transition value. I mean, the parameter value, say temperature, then temperature, or magnetic field, then magnetic field, whatever, right? Now, in this case, as we have already discussed, there is no such true phase transition, right? Pressure, entropy, everything is smoothly changing. So first of all, there is no phase transition. It's just a transition or a crossover, as they often tell. So now, so that is why it is important to call it the chiral crossover, right? Because now it depends which order parameter you are looking at, right? So depending on the order parameter through which you are looking at this transition, okay, your estimate of the transition temperature will depend, right? So, and that is fine because anyway, it's a smooth change. So now, depending on your definition, you will come up with something, right? So, so in that sense, when you take what is called as the chiral condensate, okay, chiral condensate, which is the psi bar psi, okay, expectation value, this when you take as a order parameter, okay, then using that you can estimate where is its inflection point and things like that, and you can define a transition temperature. So this temperature, transition temperature, has been estimated with the help of this order parameter, which is the chiral condensate. Okay. Now, if I may add one more information, if you were not working with physical quark mass, if you had taken the quark mass to 0, which is called in the literature as a chiral limit, right? So that's where the name chiral is coming from. In that chiral limit, this psi bar psi, this chiral condensate, would have served as the exact order parameter, very good order parameter. So it would be 0 on one side and non-zero in the other side, and hence in that 0 mass limit, you actually have a true phase transition, chiral phase transition. Okay. As you come to non-zero mass, that you no more have a true phase transition, you only have a crossover. And so, and if you use the same order parameter, okay, then you are getting this chiral crossover temperature, which is 154 plus minus 9 MeV. Okay, so this is all that I would like to tell about this temperature here, which is a very important feature of our heavy ion collision phenomenology, right? And next, once we have talked about this, now we want to explore to non-zero mu v, and if you are walking along this, so the next characteristic that you would of a curve that you would like to talk about is its curvature, right? So we know where this curve or this supposedly this transition curve, let's, if we don't want to call it phase transition, at least transition curve or crossover curve or whatever. Okay, so this crossover curve intercept we have discussed, okay, 154 plus minus 9 with this definition, right? Now we know about it. And now as you go to non-zero mu v, the next thing you would like to ask, how it bends, right? Does it bend at all? Does it remain flat, right? Does it bend the other way, or it bends this way, right? So the next property that you could talk about is the curvature of this chiral crossover temperature line, right? So this is what exactly is being written here. This is this TC mu b, TC0 mu b, right? Which is basically that at a given mu b, the temperature where this transition you are estimating via this chiral condensate order parameter. So they have done this estimate now, as I said, by these various schemes, for example, Taylor expansion scheme, by which they can circumvent the sign problem. And there are of course other schemes as well, like imaginary mu b. In the imaginary mu b, there is no sign problem. Okay, so there they can do, and then there are ways to estimate those results for real mu b. So this is the curvature, the current estimates that we have from the Lattice QCD community. So as you see that it is almost flat, right? In the beginning, it is quite flat, right? It is not, because it's some 0.0066 with error of 7, right? So it is quite flat, but then of course it starts bending more. And the thing to note is this estimate here is for these Taylor expansion methods, and this other method, there is a factor of 2 larger. So there is some still ongoing discussion about the convergence of this curvature from various methods, right? Unlike this temperature, which everyone seems to agree, on the curvature, there is still some uh, discussions, ongoing discussions, right? And then, so we have discussed the intercept, we have discussed the curvature, and then the next feature is this all important, the critical endpoint or critical point, whatever, right? So, uh, so where is the critical point? Uh, this is the two estimates that we are showing over here, right? Which are from one is here, and these are the references. This estimate is with this linear expansion method, and this one is the imaginary chemical potential, uh, and then reweighting. And you see that there is quite a large, I mean, right now there is a quite a large region over which they seem to be possibilities. So we are still to pinpoint this point, right? And so that's the location of the QCD critical point. So in this diagram, actually, if you see closely, this is the temperature axis, and this is the chemical potential axis. And here now, you now see one more parameter. I mean, this beam energy, the root is GeV, right? And these are the values. So you might be wondering where from suddenly we could on this T mu B, which are all these theoretical numbers, suddenly we start putting these experimental numbers, right? Where did we connect these two? So that will come after a few slides, maybe in the next class. So that we will come there, and right. And so in terms of the beam energy, if you look at, yeah, that's why I mentioned the beam energy. So this estimate is roughly, it's saying between 19 and 14 GeV routes, and these estimates seem to be a little lower, say 12 to 8 routes, right? And that was the main motivation, that the beam energy scan program that is being done to take, which yesterday, Professor Mohanty mentioned that the star was initially designed for 200, and then with these estimates coming, motivations came, okay, we should scan, and that's what the community has geared up to, right? And that's why we all wait for these beam energy scan results with so much anticipation. Okay, so one point about using this chiral crossover temperature, right? Because you can then ask, as we said, that because it's a smooth transition, and I mentioned that you take one order parameter, you get some number. If you get some other order parameter, you will then come up, okay, 170, 180, right? Because it's just a smooth transition. And depending on how you define, you can say this, right? So there seems a bit of arbitrariness, right, in that regard. However, what is interesting to note is if you use why this number is also important from another point of view, and that's what I would like to draw your attention to, and that is this color liberation, right? So the QCD, these two phases, the HRG phase and the Quark-Gluon phase, right? Chiral symmetry restoration is not the only thing, right? There is also this color deconfinement, right? The hadrons are colorless states, whereas the quarks and the gluons, they are carrying QCD colored charges, right? So what they did, um, or in the lattice community, um, they took these various susceptibilities, right? You remember what is this chi2b, right? For example, it is the two derivatives of pressure with respect to baryon chemical potential, right? So you're taking derivatives of pressure with respect to the appropriate chemical potentials. So what does that do for you? You see the pressure here, right? Pressure, the thermodynamic pressure gets contribution from all the degrees of freedom, right? The degrees of freedom that carry baryon charge, those that carry electric charge, those that carry strangeness charge, those that don't even carry any charge, okay? Everything will contribute to pressure, right? Now, from this pressure, which is getting contribution from all the degrees of freedom, if you are to single out the contribution of a subset of these degrees of freedom, right? Let's say you want to single out the contribution by the baryons, right? Then what you do, you just take this pressure, right? And take a derivative with mu v, for example, right? Then what will happen in this pressure, there are various degrees of freedom, we just said. Only those that are carrying this baryon charge, right? Only those will contribute, only those are sensitive to variation in mu b, right? And when you do del del mu b, you are doing what? You are changing pressure by changing mu b, right? So it's a difference in the pressure for slightly different values of mu b, right? Now those which are not baryons, they will contribute equally to the pressure. And so when you take the difference, they are gone. Except those which are baryons, they will contribute differently, right? When at mu b and at mu b plus delta mu b. So this such derivatives will single out, right, baryons. And then if you want something else, charges, then you take derivative with q. You want strange particles, then you take derivative with q. And you could take higher derivatives, then this would be even more sensitive, or that is details. But I mean, this is the idea behind taking these derivatives also, right? You could think of in this way, that they actually single out components from these all the degrees of freedom which are inside pressure. They are singling out certain class of the degrees of freedom. Okay, so that is important, right? As we are trying to discuss here. So if you now compute quantities like chi2b minus chi4b, okay, or say a mixed susceptibility. So three derivatives. If you take these combinations
Recording in
for
progress.
a non-interacting setup like HRG, you can easily show that these things will give you zero. Okay, that is what is shown here. Uncorrelated hadrons, they are giving us zero. Okay, and so that means, but in the lattice QCD, what they are seeing is that as they are changing the temperature across this regime, these quantities, okay, they are becoming, they were zero here, and then they start becoming non-zero. And you expect them to be non-zero for colored degrees of freedom. Okay, so this, then they claim that there is color liberation that is happening also in this region, in this same temperature region. So this then gives us further support that really this is an important temperature regime. It's not only that there is a chiral transition, there is also associated color liberation. Okay, and this is a very non-trivial fact, that simultaneous liberation of colored degrees of freedom as well as chiral transition, this is a very non-trivial fact. And And truly speaking, it is still not why and so on, right? And this historically, this has been a long-standing issue, whether color deconfinement and chiral restoration, should they happen at the same temperature, should they happen at different temperature, and so on. But at least these lattice results, what they tend to show is that they seem to be happening together. And hence now this 154 plus minus 9, you could think of it even more like as a spatial, right? Not just that you are using chiral order parameter, and so it is this, and you use some other order parameter, you will get a different temperature. Of course, you will get, but what this is showing that at this same temperature regime, your such kind of correlations also start becoming non-zero, signifying that now the relevant degrees of freedom are starting to be colored, right? So no more these uncorrelated hadrons will hold true, right? So so that's where we have covered with this. That's the theoretical, mostly these have been theoretical numbers. And from next class, I would like to now start making contact with experiments. So the experimental observations like mean hadron yields and then fluctuations of conserved charges, these can be measured experimentally, and then how we use these to connect with various aspects of that. So this we will then, I'll stop here and continue from here tomorrow. Okay. Is there any question?
Hi, sir. This is Ashish. So I wanted to
Hi.
ask a question on the phase diagram. You mentioned based on various model
Mm-hmm.
calculation at large mu b, the transition is a first order. And you also mentioned that following some
Yeah.
symmetry argument. So what exactly is the symmetry argument, sir?